Hi everyone, welcome to this video lecture on undamped, damped and forced oscillations and coupled oscillators part 4. In this video lecture, I would like to explain 4 short points: resonance and examples, logarithmic decrement, relaxation time and quality factor. The first topic is resonance. The phenomenon of making a body vibrates with its natural frequency under the influence of another vibrating body with the same natural frequency is called resonance. That means if a body is made to vibrate with its own natural frequency by using an external periodic force such that the frequency of upper periodic force is equal to the natural frequency of the body, then the body vibrates with maximum amplitude. Such a phenomenon is called resonance. Examples: tuning of a radio when the natural frequency is so adjusted by moving the tuning knob of the receiver set that it equals the frequency of the incoming radio waves, the resonance takes place and the incoming sound becomes maximum. That means if the tuning knob of the radio receiver is so adjusted that the frequency of incoming waves is equal to the frequency of the tuning circuit in the radio receiver is same, then the incoming sound becomes maximum due to resonance. The second example is musical instruments can be made to vibrate by bringing them in contact with the vibrations which have the frequency equal to the natural frequency of the instruments. That means musical instruments such as guitar, violin, veena, etc. made to vibrate by using our fingers at some position, the frequency, the natural frequency of the strings are equal to the frequency of upper periodic force, then the musical sounds can be here with maximum amplitude. That is due to resonance. Third example is soldiers crossing bridges are advised to march out of steps so as to avoid the resonance between the natural frequency of the bridge and the frequency of the steps of the soldiers, which may cause the collapse of the bridge. That means when soldiers crossing a bridge having some frequency, suppose if the natural frequency of the marching of soldiers is equal to the natural frequency of the bridge, then due to resonance the bridge oscillates with maximum amplitude. Due to this the bridge may collapse. So the soldiers crossing the bridges are advised to march out of steps to avoid the collapse of the bridge due to resonance. The fourth example is when an atom or molecule is struck by electromagnetic radiation having frequency exactly equal to the natural frequency of the atom or molecule, the radiation is absorbed more readily than at other frequencies. This phenomenon is called optical resonance. That means in the substance, the atoms or molecules are in vibratory position. They have some natural frequency. If the electromagnetic radiation incident on the substance, if the frequency of electromagnetic radiation is equal to the natural frequency of the vibrating atoms or molecule, then the atoms or molecule readily absorb the incident energy than at other frequencies. That is due to resonance. This phenomenon is called optical resonance. Now the next topic is logarithmic decrement. Logarithmic decrement measures the rate at which the amplitude of damped harmonic oscillator dies away. That means in case of damped harmonic oscillator, the oscillations of the oscillator decreases gradually due to frictional forces arising from surrounding air medium. So the amplitude of damped harmonic oscillator decreases gradually with the time and ultimately dies away. the amplitude of damped harmonic oscillator is equal to A into e power minus bt, where small a is maximum amplitude, b is damping quotient, t is time at which the amplitude measures. Logarithm decrement means the rate at which the amplitude dies away with the time. This can be explained as at time t is equal to 0, the amplitude A0 is equal to A. Let A1, A2, A3 and so on be the amplitudes of damped oscillator at times capital T, 2t, 3t and so on respectively, where t is the time period. That means the amplitude decreases with every oscillation. Suppose if time t is equal to 0, the amplitude is maximum, that is A0 is equal to A. After a time capital T, the amplitude is A1 is equal to A into e power minus b capital T, and after a time 2t, A2 is equal to A into e power minus 2bt. After a time A3, after a time 3t, the amplitude A3 is equal to A into minus 3bt and so on. Then if we take ratios of successive amplitudes of the damped harmonic oscillator, we get A0 by A1 is equal to A1 by A2 is equal to A2 by A3 is equal to and so on is equal to e power bt, that is equal to e power lambda, where lambda is equal to bt, where b is damping quotient or damping constant and capital T is time period. Here lambda is called logarithmic decrement. Taking the natural logarithm of the above equation, we get lambda is equal to A0 by m to the base e is equal to A1 log A1 by A2 to the base e is equal to log A2 by A3 to the base e and so on. So the logarithm decrement is defined as the natural logarithm of ratio of two successive maximum amplitudes which are separated by one time period. So the logarithm decrement represents the amplitude of damped oscillator dies away with time. Now the next topic is relaxation time. The relaxation time is defined as the time taken for the total mechanical energy to decay to 1 by of its original value. That means the damped harmonic oscillator, in case of damped harmonic oscillator, the oscillations decreases gradually with the time, so that the mechanical energy also decreases with the time. The time in which the total energy of damped harmonic oscillator decreases to 1 by of its original value is called relaxation time. The energy of damped harmonic oscillator is given by capital E is equal to half a square into k into e power minus 2bt. Here a is maximum amplitude, k is proportional constant, b is damping quotient and t is the time at which the energy is calculated. At time t is equal to 0, E is maximum, that is E is equal to E0 is equal to half a square k. Then from equations 1 and 2, E is equal to E0 into e power minus 2bt. Let tau be the relaxation time. That means the energy becomes 1 by of its original value after a time tau. Then tau is called relaxation time. Then at t is equal to tau, E is equal to E0 by E. Substituting this value in equation 3, we get E0 by E is equal to E0 into e power minus 2b tau, or on cancelling both sides E0, we get e power minus 1 is equal to e power minus 2bt. Therefore, minus 1 is equal to minus 2b tau, or tau is equal to 1 by t. That means the reciprocal of damping quotient 2b is called relaxation time. From equations 3 and 4, we get the energy of damped oscillator can be written as E is equal to E0 into e power minus t by tau. Now, the last topic is quality factor. The quality factor is defined as 2 pi times the ratio of energy stored in the system to the energy lost per period. The quality factor represents the decay of energy of amplitude of the decay of energy or amplitude of damped harmonic oscillator with the time. If Q is large, the oscillator retains its energy much more time. Q is defined as 2 pi times the energy stored in the system by energy lost per period. Q is equal to 2 pi into E by Pt, where capital E is the energy stored in the system, P is the power dissipated, and T is the time period. We know that power P is equal to E by relaxation time, where tau is relaxation time. P is equal to E by tau. Therefore, Q is equal to 2 pi into E by tau into T. On cancelling capital E, we get Q is equal to 2 pi tau by T, or Q is equal to omega tau, where omega is equal to 2 pi by T is the angular frequency or angular velocity of the damped harmonic oscillator. So, the quality factor is defined as the product of angular frequency of the oscillator and relaxation time. This equation shows that higher the value of Q, the higher would be the value of relaxation time tau, that is lower the damping. Okay, thank you.